this defense is like combined from Modelbased University here in Sweden and University of Zagreb in Croatia. My name is Ivica Crnković, and I'm the main advisor of Luka from Modelbased side, and from University of Zagreb. Maybe you can, Professor Mario Žagar.
In short, 10-year professor of computing at the University of Zagreb, Faculty of Electrical Engineering and Computing.
Yeah. So we have like shared Luka, and then we have a de facto or co-advisor, Jan Carlson, Dr. Jan Carlson. Yeah. I will just shortly describe the procedure because it will take some time so that you know what is going on. So you may know that this procedure consists of two main parts. And then the first part is also divided in some parts, but let us start. So it will start with a presentation about the work from Luka himself. So it's about 40 minutes. Okay, so you added 5 minutes.
Hi. You suggested some additional slides.
Okay, so it's about 40 minutes, and after that starts the discussion session, and then we have here the main opponent, which I would like to welcome, Professor Martin Torgen from Rural Institute of Technology. And so you will discuss with him, as you find out, it's sufficient for your curiosity or for your wish. And after that discussion and questioning, so the grading committee will have chance to ask the questions and discussing. So each of you. So I will start to present it. So Associate Professor Željko Car from University of Zagreb, Tomasz Bureš from Charles University in Prague, and Dr. Roland Weiss from ABB, Program Manager for Software Worldwide. Maybe I didn't say it precisely. Almost perfect. So, of course, they are the main person who will decide about, okay, if at the end, if this work has deserved or not deserved the PhD title. But anyhow, after the questioning from the grading committee, you as an audience, you can ask Luka, well, not anything, but almost anything. So, and after that discussion, the first part of this procedure will be finished. In the second part, so the most important part is actually we will be divided. So majority of you will wait for the results. I don't know if they will wait here or
maybe we can wait at coffee room there.
In the coffee room. Can wait in the coffee room, and the grading committee with our supervisor will have a closed meeting discussing the results of the presentation and of the thesis, and finally come to the decision, which will be then come to the coffee room, and the grading committee will announce the decision. So that's the procedure. So we have some timing constraints. I don't know, some people have flight on Wednesday or Thursday, so this procedure can take some time, but okay. So that would be the procedure. So Luka,
yes,
it's your turn.
Okay, thank you first for the nice introduction, and I would like to thank everyone who came here, especially the grading committee and the opponent, and thank you for taking time to read my thesis and to be a part of the committee. I would like to start with, again, mentioning that this is a dual doctoral degree between Modelbased University in Sweden and University of Zagreb in Croatia. And it was supported by 4 projects, thesis, Progress, Assist, and now RALPH 3. and funded by Unity for Knowledge Fund, Swedish Foundation for Strategic Research, and ABB, who is also a research partner on ASSIST project. And this will be the outline of my presentation. So first I will give some background about the context of the thesis, so embedded systems, model-based development and component-based development. And then I will give an overview of the research, stating research goals and mentioning the contributing papers. And after that, I will give motivation and contributions in 3 different areas addressed by the thesis, which are support for sensors and actuators, development of distributed systems, and analysis of system properties. And in the end, I will give a summary with a conclusion and some possible future work. So I will start with the background. This thesis was done in context of embedded systems, and these are systems, these are computer systems which are part of some bigger mechanical or electrical system. Nowadays they are really widespread, so you can find them in factory automation, in vehicles, in household appliances. And simplified, we can say that they consist of some functionality implemented by software. They are running on some small embedded computers, which we will call processing nodes, and they interact in some way with their environment using sensors and actuators. And nowadays, these systems are becoming highly complex. So every day we increase the functionality that is implemented by software in these systems. To add to that complexity, we also often have distributed functionality in the system, which means that the system is executed on multiple processing nodes connected by computer networks. And for example of that complexity of distributed functionality, in modern cars, we can now have more than 60 processing nodes connected by several networks, with hundreds of sensors and actuators, and implementing thousands of different functionalities. To make development of these complex systems easier, one thing that we can do is to employ a model-based development approach. And in this approach, instead of writing the functionality manually by developing code, we try to first make some models of the system which hides some of the details of the implementation. And in this way, the systems are easier to develop and to understand, because you don't have to take count of all the details. And then the idea is to apply automatic generation or synthesis to create these hidden details, or to create executable code. And by this, you can have a process that is less time-consuming and less error-prone than manual development of systems. Also, another benefit of using models is that you can use models to predict system properties. So a good thing about that is that analysis can be performed even before you have full system implemented and running on some processing nodes. Which means that you can test it or predict some properties early in the development. And combined with the model-based approach, we often have component-based development. And the idea about component-based development is, instead of creating all the system from scratch, to try to assemble them from pre-existing software units of software, which are called software components. So the main characteristic of software components is that they are developed for reuse. So they are developed to be used in multiple systems without us knowing in which systems these components will be used in advance. And one of the approaches to get to make components more reusable is to separate component implementation from a component interface. So we create some implementation, either by code, by composition of other components, or by some other models, and then we encapsulate it inside the component interface and hide it from the rest of the system. And then the component interface explicitly defines all the communication and the dependencies of this component. And in this way, it allows what we call black box use of a component, which means that we can use the component in different systems without knowing anything about the inside of the component, about the implementation. And for example, on the left figure here, you can see a component interface, a graphical representation of component interface as defined by the IEC 64099 standard, which is used as a base for some of the contributions of the thesis. And on the left side of this interface are two input ports which are used for communication, and on the right side are two output ports. And when you want to then use the component and make some functionality with that component, you assemble these components by connecting their input and output ports. Okay, and that ends the background, and now I will give an overview of the research. So first, research goals. Well, overall challenge of this research is how to integrate models of software and hardware in component-based development of embedded systems. And the thesis addresses 3 different areas of this overall challenge, and this is support for sensors and actuators. So how can we integrate sensors and actuators in component-based development? Then development of distributed models, in which we try to see how we can reduce the efforts of synchronizing different models during component-based development. And then also the third area is analysis of system properties, in which we explored how to use different types of models to analyze system properties. And the thesis is based on 6 conference papers. 5 of them are full papers, and 1 of these papers is short. Okay, I will start with support for sensors and actuators now. As I said, sensors and actuators are used in embedded systems to interact with the environment. So sensors are used to get some information from the environment, and actuators are used to somehow manipulate the environment. And the problem here is how to handle this interaction inside component-based models. So one of the most common approaches is to have this interaction outside of a component model, which is a valid approach, and in this way components are in no way dependent on sensors and actuators. But the problem here is that then the component-based approach, the design and analysis of these systems, does not cover the whole system. So sensors and actuators are not covered by component-based development. Then the second most used approach is to have this interaction encapsulated inside software components. And the negative side of this approach is that in this way software components can become highly dependent on specific hardware, so on a specific sensor type or how this sensor is connected to a processing node. Also, one bad thing is that then dependencies are not explicitly stated inside the component interface. And all this leads to having components which are harder to reuse in different systems. So we stated research question number 1, and this is how can we improve the support for integration of sensors and actuators in component-based development of embedded systems so that dependencies to these devices are more easily manageable. And we addressed this research question by 2 contributions. First is research contribution 1, which is a component-based embedded system model with integrated sensors and actuators. And main characteristics of this contribution is that sensors and actuators are explicit part of the model, and also that components express their dependencies on sensors and actuators on the level of interface. Also, this model is organized in multiple loosely bound layers. And here you can see an example in which we have a sensor component in the software layer, which states some dependencies on a sensor, but does not state on exactly the sensor type to which it's dependent. In the hardware layer, we have a microcontroller and a temperature sensor, which are also reusable model elements, which represent some specific controller or a sensor. And then, if we want to describe how the sensor is connected to a microcontroller, we make an allocation describing this this interaction. And then also when we want to describe, so specify to which actual sensor component inside the software model should interact with, we create a mapping in the mapping layer between these components. And if we want to change the sensor with which the component should communicate, we just need to change the mapping. We don't need to change anything inside the software layer. So advantages of this approach is first that the model gives an overview of the whole system, including sensors and actuators. It reinforces a black box view of a component by stating dependencies on sensors and actuators explicitly in the interface. Also, having multiple loosely bound layers means that software and hardware models can be developed separately, and also that the system is then easier to reconfigure. The second contribution that we made to address research question number 1 is contribution 2, which is a code synthesis method based on the proposed component models, which first defines how to assign assign predefined code to reusable model elements. And this code then implements also reusable functionality and defines how to exchange data between different elements. So for example, here to the sensor, we assign I/O component code, which defines what type of data should be returned by the sensor. To the sensor, we assign I/O device code, which implements some of the specifics of protocol communicating with the sensor. And then to the microcontroller, we assign I/O and I/O instance code, which implements the actual communication via hardware ports or pins to the sensor. And once we have assigned these code elements, predefined code elements, we can use automatic generation to create mapping code and allocation code from the mappings and allocations inside the model, which then connect these reusable model elements and implement some system functionality. Advantages of this approach is that it first allows reuse of some of the handwritten parts of the code which are predefined, and it also partly removes time-consuming and error-prone writing of code by hand for each system. This contribution has been evaluated using a prototype tool developed in the context of Procon component model, where we first defined an example system, which was a software component sending output to an LCD display, which acted like an actuator, and it was running on one microcontroller. The system was first implemented by hand, and then using the models and the code synthesis method that we suggested. And the results were, well, we first tested the applicability of modeling and synthesis, and we saw that the system was successfully modeled and synthesized, and also that the generated code correctly outputs data to the display. Then we compared the performance of generated code to the performance of handwritten one. And here I should note that we measured only the part of the code actually communicating with the LCD display, not the whole system. And we saw that execution time was 50% larger with the generated code, and also that the code size of the generated code was 6% larger than the handwritten one. And that ends the part of addressing support for sensors and actuators. And now I will go into the area of development of distributed systems. Well, as I noted, distributed systems have their functionality running on multiple processing nodes connected by networks. And when we apply model-based development to such systems, we often have possibility to describe systems with multiple models, and each of these models provides a specific view of a system. So, for example, we can describe a system using a platform-independent model, which captures the functionality of a whole system, but hides the details of communication between distributed nodes. And for example, in this figure, in the top part, you can see a platform-independent model as defined by the IEC 64099 standard. which contains 4 components, and the color of the components denotes to which processing node they are deployed to execute. So as you can see, components C2 and C3 are deployed to different nodes, but the communication between them is represented by same type of connection like the connection between C1 and C2, which are on the same node. And then we have a platform-specific model, which is in the bottom part, which describes functionality with, running on a single processing node, but also implements communication between distributed nodes. So in this model, you can see that except from components C1, C2, C3, and C4, there are 2 extra components which are used to send and receive data between different processing nodes. And there is no direct connection between C2 and C3. And the problem here is that we have separate models describing the same system. So first, we need to synchronize these models. So we need to make sure that these 2 models always show the same system, that they don't drift apart. The second problem is also that we have same parts of a system described by different model entities in these models. So the connection between C2 and C3 in the independent model is represented by a simple connection. And in the platform-specific model, this connection is represented by 2 communicating components. So we need, in some cases, we need to map these 2 together. So we need to know that the same thing is represented by two different entities in 2 different models. So we stated research question number 2, which is, how can we enhance development of distributed component-based systems in order to reduce the effort of synchronizing platform-independent and platform-specific models? And we addressed that question with research contribution 3, which is a method for automatic generation of communication components in distributed embedded system models. So first, the first characteristics of this contribution is that we automatically generate communication components in platform-specific models. And we do that by extracting all the needed information from the platform-independent model and the model of platform. And also, besides just creating communication component, we create annotation or notes in both models describing which components are generated for which model parts. Also, the contribution is implemented in form of a framework with separated phases or modules, which have well-defined inputs and outputs, and which can be easily exchanged. So advantages of this approach are first that platform-independent and platform-specific model in this case can then be automatically synchronized. And also that annotations can be used to further synchronize the models or map, create mappings between model entities inside the 2 models. Also, because we have a flexible framework, framework separated into multiple phases, the generation method is quite flexible and can be extended easily with new protocols or new communication components, or can be adapted to different component models. This contribution was evaluated using a prototype tool, which was implemented for the IEC 64099 standard, and it is a part of an open source for DIAC integrated development environment for this standard. The tool was first applied to an extended example that we devised, and then we applied tool to 4 different applications, case study systems, to 2 case study systems, which are taken from an external example library, and from which we, before applying the tool, removed the original communicating component. So the results of the evaluation are that we first did an applicability test on the extended model, and we manually inspected the generated components, and we saw that they fit our expected results. And then we did the applicability test on the case study systems, where we first manually compared the generated communication with the original, and we saw that the generated components are in line with the original ones, although the original ones had some implemented some optimizations which were not present in the generated components. And also, excuse me, the functionality of the system with generated components was manually compared to the original system, and we saw that the system provides in both cases the system provides same functionality. Okay, and now I will talk about the area of analysis of system properties, where we have a problem that many embedded systems have real-time constraints, which means that they have to provide their functionality on time, or they may fail or even cause some accidents. Example here is, for example, an airbag system inside a car, which if it's not deployed on time, it will just not work. It may even cause more damage than good. So verification of this real-time constraints is based on the analysis of worst-case execution time. So worst-case execution time of some functionality is the largest possible time that will that some processing node will take to execute that functionality. The problem is also that this analysis is traditionally performed in late stages of development. And problem of that, again, is that finding problems in late stages of development can lead to extensive refactoring. So large changes which can cost a lot of money and can take a lot of time. So we stated research question number 3, which is how can we utilize software and platform models to efficiently analyze extra functional properties of component-based systems in early stages of development. This research question was addressed by research contribution 4, which is a method for compositional timing and utilization analysis of component-based systems. So this analysis method was developed in context of the 4099 standard and is quite specific for that standard currently. And it is separated into 4 methods. 3 of them are worst-case execution time analysis methods for different parts of the model. And also we have analysis of processing node utilization, which is based on the worst-case execution time analysis. Characteristics of this is that we use a compositional analysis approach, which I will describe later. And also that we support analysis of models containing cyclic execution paths. And about this part of the contribution I will not talk because of the short time for the presentation. So this figure gives an overview of the analysis. So in the bottom we have a basic component reset analysis, which is performed on software models. And then results of this analysis are used by the composite component analysis combined with, again, just the software models. And then we have a node-specific application worst-case execution time analysis, which uses both previously mentioned analysis methods, results of these methods, but also extends the analysis to deployment model and the platform model. And then at the top, we have a processing node utilization analysis, which takes, again, into account results of all these other 3 analysis methods, but also takes into account information about trigger periods of execution triggers inside the system. Sorry. Okay, and I will start with basic component analysis. So it's based on analysis of an internal execution control chart, which is shown in the figure right here. And I will not also talk about this chart or details of the analysis. But what I will mention about this is that the analysis determines all possible execution paths starting with some event input. And the result of this analysis is context-independent worst-case execution time data for components. which is stored together with the component interface. So this data describes all possible paths inside the component, which can lead to worst execution time of a system on the level of component interface. And once we get this data for a component, we do not need to do any reanalysis of the inside of the component. We have everything on the interface level. And also, what makes it context independent is that each path contains worst case execution time value, but also it contains information about generated outputs. So in this way, we can try to see how the execution of a component will affect execution of the whole system. And in the figure left here, we can see the graphical representation of this data. So with input event I1, we can have two different execution paths. One has a worst case execution time of 10 and leads to one output at output port 1. And the second one has execution time 8, but leads to one output at O1 and one output at O2. And when looking at this component independently from a context of any system, we do not know which of these will lead to worst case execution time of the system, the one with larger execution time or the one that generates more outputs. Okay. Then on top of this, we built composite component analysis, which is based on analysis of internal component network. And it uses the existing worst case execution time data defined for the components inside the composite. So we use the connections and the data that we have for our components to explore all possible execution paths. And also one of the problems here is that these parts, because we have different alternatives to execution inside component, these paths can fork and have multiple alternatives. So even in this small system, we have 4 different execution paths. The result of this analysis is, context-independent data for the composite component. And in this way, once we analyze the composite component, we again don't need to go inside the composite again. We just use this data when this component is used on another level of hierarchy. And I should mention that although I said that there are 4 different execution paths inside the composite, here we have only 2 execution paths on the interface, which is because during the analysis we can find some execution paths which we know that will not lead to worst case execution of a system, and we can remove these paths. And in this way, we can reduce the number of paths we need to analyze during the whole system analysis. And then we have node-specific worst case execution time analysis, which is similar to the composite analysis, but it combines platform-independent model of software with the model of deployment and the platform. So in this case, interesting thing is that different execution paths can result in a worst case execution time for different devices. So for example, if we take this system without any deployment information, we can see that the worst case execution time path goes from C1 to C2 and to C4, and we have a reset value of 115. But if we take into account deployment, so now if we want to analyze just processing node number 1, the worst case execution time goes from C1 to C2 and then to C3, and has a reset value of 85. So this is the worst case execution on processing node number 1. Then if we analyze processing node number 2, we see that we go back to the path from C1 to C2 and then to C4. But the worst case execution for this node is only 100 because C1 and C2 are not executed on that processing node. But we still take into account the path of execution through the through other processing nodes. Advantages of this approach are that first analysis analysis using models can be performed before the system is deployed. So we can predict system properties in early stages of development process. Then, as we use the compositional analysis approach, it allows us reuse of analysis results for components. So we need to analyze each component only once unless something inside it changes. Which also means that changing some part of a system does not require a reanalysis of the whole system, but just that part that changed. Also, it gives us then high performance or low running time of the analysis, which in turn allows the analysis to maybe be used more often. Also, the analysis combines platform-independent and platform models. So we can, by this, we can explore all execution paths inside a system from the platform-independent model, but we can also find worst-case execution paths giving some specific processing node. This contribution was also evaluated using a prototype tool implemented for the DIAC development environment for 1499 standard. The tool was applied to 4 applications, which were taken from an external example library. And also the cyclic execution path analysis that I didn't talk about in the presentation was tested on 16 test scenarios where we had predefined models with some expected results, and then we applied the analysis to these models. And the results were, first we tested the applicability of analysis. So the analysis could be performed on all the example systems. We also measured the analysis performance. So for the largest system, which consisted of 60 component types, 158 component instances, and 6 levels of hierarchy, the analysis time was around 12 milliseconds. Also, the test of cyclic execution paths resulted in, well, the analysis results matched the expected results for all test scenarios. Okay, and now I will give a summary. First, a conclusion. So I've presented how in this thesis we did integration of sensors and actuators in component-based development, which reduces dependencies of software components on hardware, on sensors and actuators, and in this way gives more potential for component reuse, and it also allows easier reconfiguring of the system because changing one part of the model doesn't mean that you have to change another part. Also, I've presented a framework for automatic generation of distributed communication in component-based models, which allows automatic synchronization of platform-independent and platform-specific models. And also, the modularity of the framework makes the generation easily extendable to different protocols or adaptable to different component models. And also, I have described a method for model-level timing and utilization analysis, which is performance effective and applicable in early stages of development. And also, this analysis combines platform-independent and platform models to get some platform-specific results for timing and utilization. Now for some possible future work, and one of it is the use of models containing sensors and actuators for analysis. So the contribution number 1 and contribution number 2 allow us modeling sensors and actuators and automatically generating or synthesizing code for communication with them. And also, although I didn't mention it, the modeling method allows specifying some extra functional properties for model elements. But the method does not handle how to perform analysis of models containing sensors and actuators. So one possible future work would be to extend work with that. Then we could, the worst case execution time analysis method that I've presented could be applied to models annotated, to platform-specific models which are annotated with information about connections inside the platform-independent model. So the current analysis is only performed on platform-independent model. It does not take into account components which are in platform-specific model. And by taking into account these annotations, we could connect these two models maybe, and then perform some more precise analysis of systems. Also, the worst case execution time analysis could be extended to take into account data flow. So the analysis I've presented only takes into account events or control flow inside the system and does not take into account how data is transferred or the data values that are transferred between components. So also by taking into account these values or this information, the analysis could maybe be more precise. Okay, and that's it. Thank you for the attention. I think it was a bit less than 40 minutes.
Thank you very much.